Okay, thank you, Lucio, for the invitation to give this seminar. Thank you, everybody, for the opportunity. I will talk a little bit about this work we did in the last 2 years. Basically, this was the PhD thesis of Denilson Toneto, that was a student from the University of Santa Maria, and part of the work was did by all these people, and actually this work is was published in 2 papers, and I will show you later. What is the motivation to study? Because the title of the seminar is Stabilization of Skyrmions on Platinum, Cobalt, Tantalum, Multilayers, and Arrays of Nanodomes. What are skyrmions? Skyrmions are magnetic entities that have received a lot of attention in the last years, mainly because they can be used to store and read information in new magnetic medias, like this example here. They call this racetrack memory, but in this case, some years ago, Parkin from IBM proposed these racetrack memories, but they proposed it using the domain walls, and now they discovered that skyrmions that are circular and more stable than domain walls can be much more easy and much more feasible to be used in these racetrack memories. The basic principle should be, okay, you nucleate a skyrmion. I will talk a little bit more about the skyrmion. A skyrmion is a circular domain, a circular magnetic domain that has this form. And the idea is to nucleate a skyrmion and propagate the skyrmion around the racetrack by current pulses. And if you have a skyrmion, you have a byte 1. If you don't have a skyrmions, you have a byte 0, and so on. So you can read the skyrmions, and you can change the polarity of the skyrmions, whatever, by current pulses. Some setups have already been tested in some tracks like this, and they managed to generate small skyrmions, not so small, but micrometer skyrmions, and to propagate them on tracks. And the skyrmions are similar to other domains in magnetic materials like vortex or anti-vortex, but they are a little bit different because and they can be more stable. Okay, a skyrmion originates from, especially in multilayers, in magnetic thin films, it originates from the interface of a magnetic material with a heavy metal that have a large spin orbit coupling. And when you have the magnetic material that is represented here by the gray color in contact with a metal with a large spin orbit coupling, like this blue one, and you have a mechanism that is called Dzielorinski-Moria interaction between the spins of the magnetic material and the spins of the heavy metal, that makes the spin rotate 90 degrees from the direction of the two magnetic spins. You have a rotation of the spins that is 90 degrees, and this makes that the skyrmion will have spins that will rotate from, like in this example, this is a neo-skyrmion, will rotate from outside to inside of the plane in a very odd manner, very differently from the normal rotation you have when you have a vortex, for instance. In this case, you have this is a neo-skyrmion. There are also block skyrmions, but this makes the skyrmion very stable to defects and makes this very easy to move by current pulses, for instance. And of course, the skyrmions can also be affected by magnetic, electric fields, and can also suffer from Hall effect. Skyrmions in magnetic multilayers are based on usually occurs in the transition in the interface between a heavy metal and ferromagnetic material. Yeah. Systems with structural inversion symmetry. They originate from the Jalorinski-Moria interaction that is have this equation, and is represented by this orientation of spins. You have to have heavy metal with a strong spin-orbit coupling, yeah, that will lead to antisymmetrical exchange. That is known the Jalorinski-Moria interaction. This interfacial Jalorinski-Moria interaction plays a key role in the stabilization of chiral spins structure. The skyrmion's nucleation and stabilization in most cases require external magnetic field or electrical current. So it's important to control the external field or the current to nucleate skyrmions. And it has been observed that structures that are made by lithography or confined structures are more more easy to observe skyrmions on these kind of structures, like this one. You can see that in this example, if you decrease the size, the diameter of the dots, you are the authors have been able to stabilize skyrmions on the center of the dot. This means they could change the configuration from stripe domains to skyrmions by decreasing the size of the dot. And the skyrmions can also be suffer from some typical problem from that is the skyrmion Hall effect. This means that if you apply a current and a field, a perpendicular field to the track, the skyrmion will change the direction. Instead to go from left to right or right to left and cross all the track, they will move to the border of the tracks and can be annihilated in the borders of the track by the skyrmion Hall effect. So skyrmion Hall effect is an important problem you have to solve before to have a practical application. Given all this motivation, the skyrmion Hall effect can be extracted from the difference between the magnetization and Hall effect curves, and we can also use the name of the that is given to the Hall effect that is affected by skyrmions. Usually is topological Hall effect. It comes from the last part of this equation. This is the equation of extraordinary Hall effect in magnetic materials. There is one part of this Hall effect that is proportional to field and proportional to the resistance. The second part is proportional to the magnetization that is perpendicular to the field, especially in perpendicular in multilayers that have perpendicular anisotropy. And the last part is the contribution from the skyrmions to the Hall effect. This part can be extracted from the difference between magnetic and Hall effect curves. And usually the peaks that appear on the topological Hall effect can be associated to the nucleation of skyrmions, as you can see here on these MFM image of the films. Based on this, the Nilsson prepared in the PhD thesis several multilayers of platinum, cobalt, tantalum. As you can see here, the cobalt is magnetic material, platinum is a heavy metal that is in one side of the cobalt. The other side of the cobalt, we use tantalum. That is another heavy metal with a different spin-orbit coupling. So both heavy metals on both sides of cobalt have different spin-orbit coupling and help to increase the Jalorinski-Moria interaction and to induce the presence of skyrmions on this kind of multilayers. He prepared several samples with different thickness of cobalt, like 1.3 nanometers to 2.1 nanometers, increasing the thickness of cobalt. And what we can see on these hysteresis curves, the A curves are measured perpendicular to the plane of the sample. That means with the field perpendicular to the sample. In this case, when the thickness of cobalt is small, like 1.3 nanometers, the hysteresis curve is more vertical, and this goes to horizontal as we increase the cobalt thickness. This means that the samples that have smaller thickness of cobalt have more perpendicular to plane anisotropy. Here is in B, you can see the hysteresis curves measured in the plane. You see the opposite behavior from A to B. And on C, you can see the anisotropy, the effective anisotropy of the samples that is measured, basically measuring the field that is necessary to saturate the sample in out of plane or in the in plane, depending of the easy access of the sample. I forgot to put the equation here, but it's simple. A simple relation between this field, you can get the anisotropy, and the samples that have lower cobalt thickness have higher anisotropy. That is, when the anisotropy is positive, this means the anisotropy, the easy axis is out of plane, is perpendicular to the plane of sample. And when the anisotropy is negative, means that the easy axis is in plane of the film. So the films with the different thickness change the anisotropy from out of plane for 3 samples to in plane for the last 2 samples. And this sample, the intermediate sample with cobalt 1.7 nanometer, is the sample that has intermediate anisotropy. The smaller anisotropy, is the sample that is in the transition between in plane and out of plane. This is still out of plane, but is almost in plane sample. And we can see here the MFM, the magnetic force microscopy of the different samples. And we see that different samples means I don't have the caption, but D is for 1.3, E is for 1.7, and F is for 1.9. And you can see here that the E sample, the 1.7, has smaller stripe domains and several isolated domains that could be skyrmions, that they are very small. And on the other samples, you don't see this. This is in the demagnetized state. Okay, let's go on. This sample, this paper was published on this journal. Okay, if we measure the Hall effect, we have the same behavior. The Hall effect is measured by the voltage in 2 branches of the cross. when you apply a current in the other branch and you have a perpendicular field perpendicular to the sample. If you have skyrmions, you can have some contribution from the topological Hall effect, and you can basically you can have the external hysteresis curve similar to the magnetization hysteresis curve from Hall effect, because you have a strong contribution from the magnetization perpendicular to the plane. So the Hall effect is very similar to the perpendicular hysteresis curve for this kind of sample. And you can make several internal curves like this protocol here in the first figure. You reverse the field and measure again the internal curves inside the hysteresis loop. This protocol is called first order reversal curves. Yeah, you can do this by magnetic measurement or by Hall effect measurement. If you do a second derivative of the magnetization or the Hall effect curve as function of the fields you use it for the creation of this curve, you can have this diagram that is shown here in blue, where you have this diagram is plotted as a function of reversal fields as a function of applied field. The reversal fields are the fields you use to reverse the magnetization or the Hall effect, like this HA plus delta HA, and so on. So every field here where you start this internal curve is a reversal field that is plotted here in the left. Okay, and the applied field is the field that you applied. It's the same field as in the hysteresis curve or in the Hall effect curve. So in this kind of Hall curve, where you have two parts of the curve that are broad, like this one and this one, the same region will transform in a maximum in the first order diagram, like this one and this one, that are red or yellow, that have a higher intensity. And they are associated to regions where the magnetization process is irreversible. That means after you apply a reversal field that cross this region, this field, like more than minus 500 Ersted or more than minus 50 Ersted, you have a magnetization process inside the sample that is irreversible. That means you cannot come back to the magnetized state from this state. And there are several authors that reported that this irreversible magnetization process can be associated to the stabilization, to the nucleation and stabilization of skyrmions. And what we did, we mapped these reversal fields for two samples, 1.3, 1.7, and on sample with a cobalt thickness 1.7, we mapped different reversal fields inside only one branch of these reversal fields. And we did a magnetic force microscopy on the sample for different reversal fields. That means we come to HR1, that is 500 minus 500 Ersted, and come back to zero field, and measure the MFM, and we observe these stripe domains. If we increase the reversal fields, what this means? I take the sample, I applied a reversal field of minus 1000 Ersted, and remove this field and put the sample in the MFM with zero field. and observe this in image 2 that correspond to this red dashed line in the image. And we see a lot of skyrmions. The same happened in 3 when we applied 1050 500 Ørsted. We see a lot of skyrmions. But if we go to the saturation of the sample, HR4, we come back to the stripe domains. That means that you can find appropriate fields, reversal fields, that you can apply to the sample, come back to the zero field, and observe skyrmions. The skyrmions nucleate and stay stable in zero field for this kind of sample, and you can discover what fields are these appropriate fields by doing the first order reversal curves in Hall effect or in magnetization. Okay. The next work we did was to use a mechanism we developed some years ago to have a modulated substrates for the position of thin films. The modulation is done by anodization of aluminum. We take a piece of aluminum, we make the anodization with acid in a controlled way, and we get in one side of the aluminum, we have a alumina membrane that in one side we have holes, ordered holes. The other side we have ordered nanodomes. And this membrane is made of aluminum oxide, is an insulating membrane, and we can use this to deposit the multilayers on top of this part or in this part, and we will have modulated multilayer. Some authors published some papers with theoretical predictions that says that curved surfaces can also help to stabilize skyrmions. So we did what we did. We deposited the same multilayers, platinum, cobalt, tantalum, 15 repetitions on top of these nanodomes, arrays of nanodomes. This is a scanning microscope image of the arrays of nanodomes with the nanodomes of 100 nanometer in diameter. And we have the stresses curves of the reference sample. That means the sample on the continuous film, the flat film, in plane, out of plane. We have different anisotropy. And on the nanodomes, we observe that in the out of plane, we have a higher coercitivity. We don't have anymore these two larger parts of the curve, very typical from the multilayers. We have this in a smaller, in a much weaker this behavior. The anisotropy also decrease in the in plane and out of plane are more similar. We did MFM image of the samples. In the reference sample, we observe large stripe domains that are 300 nanometers in size. And if we have the MFM image of the nanodomes, as we can see here in C, we see that the stripe domains are restricted to the size of the nanodomes. We can see even here in some part, we can see very small domains that that are exactly the size of the nanodomes, 100 nanometers. Could be skyrmions or not, or could be chains of skyrmions on top of nanodomes. So this is true. We can also nucleate skyrmions on top of these nanodomes, as the theoretical works predicted. And we did some simulation. The simulation agreed very well with the experimental image. This is the simulation of the continuous film, and this is the simulation for the nanodomes. And we can see the same behavior from the experimental MFM curves, images. And we applied some magnetic field to the samples with the nanodomes, 50 millitesla, and go to zero. That means apply the field, observe a lot of skyrmions that nucleate on top of the nanodomes, go to zero, and on zero field, without in the remanence, we still see several skyrmions that remain stable on top of nanodomes. If we apply a larger field, 70 millitesla, we still have a lot of skyrmions, less skyrmions than the previous field, and we still see some skyrmions that remain stable on top of nanodomes, but we also see that the stripe domains increase, the number of stripe domains. And if we apply a larger field, more close to the saturation, we nucleate few skyrmions, and most of the skyrmions become stripe domains when we go to zero field. This is related with the reversal fields we see for the continuous samples. We have another work that related the fork curves for this kind of samples. We will publish this, I hope, next year or this year. I have to finish this paper. But we have the same results of fork for this kind of sample also, that relate this, why we observed we have to apply these fields to stabilize the skin. And we did simulation. The simulation agree very well with the experimental the observation MFM. And we also can see that we can nucleate skyrmions depending of the part of the hysteresis curve we are. We also simulated the hysteresis curve by doing micromagnetism. We see that in the continuous film, we nucleate a skyrmion, we remove the field, and the skyrmion become grow in several stripe domains. If we stabilize a skyrmion on the nanodome, we remove the field, and the skyrmion stabilize on the nanodome like this, because the borders of the nanodome avoid the growing of the skyrmion in stripe domains. We tested this on continuous samples to see if the mechanism, and we see the same. In the continuous sample, we nucleate the skyrmions by field. We remove the field, and the skyrmions grow. And this is not the same. This is the sample 1.3, not the 1.7. So it's the sample that doesn't stabilize the skyrmion very well. And we did simulation, and at the end we proposed this kind of racetrack, not a racetrack. Basically, we proposed this. This is some way to stabilize skyrmions on a racetrack made of nanodomes, but by a localized magnetic field, like the one we can generate with a MFM tip. We can nucleate a skyrmion on some position, and if we move the track or the tip, we can nucleate several skyrmions, and they will become stable on top of the surface. We did a simulation of this that is here. This is a simulation of this racetrack where we can nucleate skyrmions, and they remain stable on this racetrack by the localized, and we can nucleate and erase the field, the skyrmion with the localized field. Okay, thank you very much.